So Newton's first law is that an object at rest remains at rest, and an object in motion remains in motion at a constant speed and in a straight line unless acted upon by an unbalanced force. So say we have this box here that is at rest on a surface. So we have the force of gravity here. This can sometimes be called W. So that is pulling this box down. But because it's at rest, we know we have to have some force opposing that equally. And that is what the normal force is. This can also just be called N. So when we write our net equation, we get our F net is equal to our normal force plus our weight. F net is 0 because the object is at rest. And we get that the normal force equals the negative weight, which makes sense. It's directly opposing our force of gravity. So when we expand this out, we get negative mg. And it's important to note that this is where g is equal to negative 9.8 meters per second squared. So when you're given n equals mg, this is almost always using g equals positive 9.8 meters per second squared. So Newton's second law deals with the case where the net force is not equal to 0. In this case, we have non-uniform accelerated motion. So in this problem, we're given a block that is moving right on a surface. We have a coefficient of static friction of 0.2 and a mass of 2 kilograms. Just a reminder, the force of friction that opposes this block is equal to mu times the magnitude of our normal force. So given this, try to find the magnitude and direction of the acceleration of this block. So we have 3 forces acting on this block. We have our force of gravity here, our normal force, and this force of friction. So these 2 vertical forces cancel out, which just leaves our net force equals force of friction. So our net force is always equal to ma, and our force of friction down here is equal to mu times our normal force. Since this normal force is equal and opposite to our force of gravity, we can break it down even further to mu mg. So our m's cancel out, and we're left with a equals mu g 9.8 meters per second squared. And we're left with our final answer. So it's a pretty simple problem. Let's look at something a little trickier. So this problem might look familiar. We're given 2 blocks, a bottom block of 2 kilograms and a top block of 1 kilogram. We assume that there's a rough surface between these two that allows the 1 kilogram block to stick. So our goal is to find the minimum coefficient of friction such that when this force is applied, this block will move along with the bottom block. So give this a try on your own. So let's write our variables down first. So we start by finding the acceleration of this system. So remember, F equals ma. Because these 2 blocks are attached by friction, we can really just treat it as one object. So our force equals mass 1 plus mass 2 times acceleration. Rearranging, we get this, substitute, and there's the acceleration. So for the next part of the problem, we're going to have to draw the diagram only for this top block. So for this small block to accelerate along with our entire system at this same acceleration, it needs to have some force here with an acceleration equal to the one we found here. So we have to remember the two other forces acting on us. We have force of gravity, normal force. Just like our previous problem, our normal force and our gravitational force are equal and opposite. So we can just equate like that. So then we have to consider what this force actually is. So what this is our force of friction, specifically our force of static friction. In most problems, we think of the force of static friction as directly counteracting some applied force. In the case of this problem, that force is actually counteracting this top block's tendency to want to stay still. That's Newton's first law. This object wants to stay at rest, but it can't because it's being pulled along by this force of friction. So our force of friction is always less than or equal to the coefficient of static friction times the magnitude of our normal force. So bring this down, we get force of friction is less than or equal to mu times mg. Also have to remember our net force right now is just equal to our force of friction. So that itself is equal to mass times acceleration. Remember here that we're specifically talking about m1, not like in the first part of this problem where we consider this as one object. So ma is less than or equal to coefficient of friction mg. These two m's cancel, and we get mu to a over g. So our final answer for mu is about 0.3. That's all there is for this section.